The course is Digital System Design. As the name implies, this course is going to cover design of digital circuits or digital system. I suppose you all are able to hear me, right? Please confirm once. Yeah, okay. Okay. So you see any electronic circuit can be broadly classified into either as an analog circuit or as a digital circuit based on the signals that they process. To put in simple words, analog circuits deals with continuous analog signals, whereas digital circuits deals with digital signals. In the sense, analog circuits process analog data. On the other hand, digital circuits accepts and process digital data. You all must be knowing what is the difference between analog and digital signal, right? Analog signals are continuous time varying signals. Almost all the signals in the world are analog, like sound, temperature, pressure, etc. Digital signals, on the other hand, are time-separated signals. It deals only with two logic levels, that is logic level 0 and logic level 1. So if you measure the quantity at any particular given amount of time, you will find that the value will be either 0 or logic level 1. Even though all the physical signals of the nature are continuous time varying analog signals, but representing signals in digital form has lots of advantages. Digital signals can be processed in a better way than that of analog signals. Digital data can be compressed very easily. Information in digital form can be encrypted. So these are few of the benefits of digital signals, and therefore you will find that most of the systems are now they comprise of digital circuit more. Okay? The ICs contain more of the digital part rather than analog part. Okay. If you look at the circuit of digital system, at low level, the digital circuit consists of combination of transistors or logic gates, and at high level, it consists of microprocessors or microcontrollers. So in this course, you are going to learn about various aspects or various concepts that will help you in understanding how to build digital circuits basically. The prerequisite for this subject is basic electrical engineering, which you have already undergone during your first year of engineering. The objectives and outcome of these courses are like this. I'll just read the objectives. The objective of this course is to introduce different digital codes and their conversions, to introduce various methods to reduce logical expressions, to make you aware of the design steps for designing combinational logic circuits as well as sequential logic circuits, and to illustrate the concept of programmable devices. So on completion of this course, you will be able to identify various digital codes and you'll be able to convert the digital code from one form to other form. You will be able to reduce the logical expression using various reduction techniques. You'll be able to analyze and design both combinational as well as sequential logic circuits, and you'll be able to classify different programmable logic devices. So before I start with this course, let me just take you through the syllabus, okay, so that you understand what will be covered in each unit of this course. So the first unit of this course basically deals with digital codes and binary arithmetic. Okay? So here in this unit, you will learn various digital codes which are available, and you will learn how to convert from one code to other digital code. Once you have knowledge of various digital codes and binary representation, you will be taught about how to perform binary arithmetic operations. Okay? In the sense, I will first of all be explaining how to represent signed binary numbers. In that sense, what I mean to say is that how to represent decimal numbers which are associated with sign in binary form. So basically there are three ways to represent negative numbers in binary. Those are sign magnitude representation, ones complement representation, and two's complement representation. So you will be learning about these ways to represent the signed binary numbers. And then we'll see how to perform arithmetic operation, that is addition and subtraction operation on the signed binary numbers. Okay. This is about the first unit of the course. The second unit of the course comprises of various fundamental concepts that will be required to be applied while designing the circuits, digital circuits. So this here you will be introduced with various logic gates, and you will learn how to realize, how to represent any digital circuit. There are various ways to represent digital circuits. Okay. For example, by means of truth table or by writing the logical expression for that circuit. So you will come to know about all these various ways to represent the digital circuit. And then you see, as I said, one of the way to represent a digital circuit is by means of a logical expression. So normally when you have to design a digital circuit, from the logical expression, we do not implement the circuit immediately by looking at the expression. The expression is always, reduced, and then the minimized expression is implemented. The reason for this reduction of the Boolean expression is so that the number of amount of components required to make the circuit will become less, and therefore it will be more cost effective. Okay. So you will learn various techniques which are used for minimizing the Boolean expressions in this unit. Okay. So once you have you gain knowledge of these basic concepts, then we will move to design of digital circuit. You see, any digital circuit can be classified either as combinational logic circuit or sequential logic circuit. Now you must understand what is the difference between these two logic circuits. Okay? To explain this in a very briefly, combinational logic circuits are those digital circuits whose output at any given point of time depends on the current input applied to that circuit. For example, you take any logical gate. If you know about logic gate operation, you will know that the output of this logic gate is always function of what the input applied to that gate at particular amount, particular time. So output, when it is function of input applied to the circuit, it is called combinational logic circuit. Okay. On the other hand, we have sequential logic circuits. Sequential logic circuits are those digital circuits whose output at any given instant of time not only depend upon the current input applied to the circuit, but also depends upon the current state of the circuit or the current condition of the circuit. Okay. As an example, the smart TV system is an example of sequential circuit basically. The TV remote, you see, has a channel up and channel down button on it, right? So to know which channel will be displayed on pressing these buttons, it must have knowledge of which channel is being viewed at that time, which means it must know the current state of the system. So thus the channel that will be displayed on changing the input through the remote control depends upon both input, that is whether you are pressing channel up button or channel down button, and the current state of the system, that is the knowledge of channel that is being viewed at that time. Okay. So such kind of systems are called sequential logic circuit system. Okay. Wherein the output of the circuit is function of both current input applied to the circuit and the current state of the circuit. Current state of the circuit in turn depends upon the history of past inputs applied to the circuit. So from the construction point of view, every sequential logic circuit should have some kind of memory element which will store the condition of the circuit at that time. Okay. So the basic building block for combinational logic circuit are logic gates, and the basic building block for sequential logic circuits are the flip-flops, which are 1-bit memory elements. Okay. So the third unit of this course will cover the design of combinational logic circuits. Okay, so you will learn how to design various combinational logic circuits such as code converters, adders, some kind of fast adder circuits. The unit will also cover design of some of the very special circuits which are also available in integrated circuit forms, so that they can be used to design more complex digital circuits such as multiplexers, demultiplexers, and decoders. So we will also learn how to design and use multiplexers, demultiplexers, and decoder circuits, which are also available in IC form in market. Next unit covers sequential logic circuit design. Here you will learn how to design sequential logic circuits. So before you learn about sequential logic circuit, you will be taught about the flip-flops, various types of flip-flops, how the flip-flop work, and then we will use the flip-flop and design various sequential logic circuits such as counters, registers, etc. Also, you will be introduced to state machine concept, wherein you will be taught how to design sequential logic circuit from state machine perspective, or in fact there are two very common representations of sequential circuits. One is Mealy's machine, another is Moore's machine. So you'll be learning about how to design the circuits using these two kinds of representations. Okay. And the last module is about programmable logic devices. You see, there are large varieties of ICs available in the market which can be programmed as per the user's wish. Okay. So in order to program such kind of ICs, you must know some hardware descriptive languages, some programming languages, which can be used to describe the circuit. And once you have the program, you can configure the IC as per. So the IC will start behaving as per the program that you configure into the IC. So these kind of ICs are called programmable logic ICs. There are different types of programmable logic ICs like PROM, programmable ROM, PAL, PAL, that is programmable array logic, and PLA, which stands for programmable logic array. Okay. In order to expand the size of programmable logic array, different companies were working on it, and two companies came up with
Ma'am, we aren't able to hear you.
must know the general architecture of
Yeah, ma'am.
Not able to hear me? Just a second. I'll just open it. Okay. Are you people able to hear me now?
Yes.
Yes.
Hello?
Yes, ma'am.
Okay. So, programmable logic devices, which is the fifth unit of the course. Here you are going to learn about various programmable logic devices and how to use these devices to build digital circuit. Okay. So there are certain varieties of ICs available in the market which can be programmed as per the user's wish. And these kind of ICs are called programmable logic ICs. So programmable logic ICs can be broadly classified into PROM, PAL, and PLA. PROM stands for programmable read-only memory. PAL is programmable array logic. PLA is programmable logic array. So in order to expand the size of PLA, two different devices came into the market at about the same time. One was FPGA, other is CPLD. FPGA is field programmable gate array developed by Xilinx company, and CPLD is complex programmable logic devices developed by Altera company. Both these companies had developed and launched the product almost at the same time. Okay, so these are very complex circuits, very complex integrated circuits which are programmable in nature, so that the user can configure these ICs as per his or her wish. Okay. So this is about the course. Now let me also tell you a few of the things before I start with the syllabus. First is that I want you people to make a separate book for this course, and please take down whatever I am explaining during the class. Okay. Second thing is, after completion of every unit, there will be quiz. Quiz will be conducted, and the quiz will be evaluated, and its marks will be counted for evaluating the term work. So the marks of this quiz will directly be attached to the term work of your term work marks. Okay. So after completion of every unit, I will give you the prior notice that tomorrow maybe it's the last lecture, and then there will be quiz like that, so that you are well prepared. So, and the quiz will comprise of questions based on whatever I'm teaching during the class. Okay. So this is about the syllabus. Um, the third column here, as you can see, is the duration. This is the estimated time, or the time that will be required to cover the unit. Okay. So apart from this theory, there is a lab or component also associated with this course. As I said during the orientation of your class, in the lab, as I said during the orientation, there will be total 8 experiments, and there is one mini project also. So I will tell you what is to be done in the mini project later on. But the experiments will be conducted in the simulation tool. Okay. And the approach that I'm going to use to conduct the lab is, I will first of all explain you the software, how to use the software, and I will show you how to design the circuit using the software and how to see the output as well. Okay. Now what I would expect from you student is that when once I explain a concept, I will give some additional part of it which you have to do on your own later on. Okay. For example, let's say I explain how to design. There are two universal gates you all must be knowing. NAND gate and NOR gate are the universal gates. So I will explain how to realize a logical function using NAND gate, and then I'll ask you people to realize the same function using NOR gate. So the concept will remain same. Only you will have to apply that concept in doing the second part of the problem. Okay. And then later on maybe we will discuss it how you have done and all. Okay. So one part I will totally explain, second part you will have to do and show me the result. Okay. Of course, first part also you will simulate, and in addition to that, second part also you have to do. Okay. I think it is clear. Similarly, let's say one more example. I'll explain how to design a full ladder circuit using half adders. Same concept you have to apply to design full subtractor circuit using half subtractors. So the concept remains same, only you must, there are two purpose of doing this. One is that you will be attentive, you will listen how it has to be done. Okay. And secondly, you will apply your own mind and come up with the solution. Okay. So this is how I'm planning to, conduct the labs. Also, few of the experiments will be recorded. I will actually take the breadboard and will mount the circuit on the breadboard and will show you the output through the video recording. Okay. So that you will come to know you will understand how it has to be done practically also. Okay. So this is about the content of the course. So let us now start with the course. Okay. लाइट नहीं आ रहा है, देखो कितना शैडो आ रहा है यहाँ पे। क्या Can you people see the screen properly?
Yes.
Yes.
Yes, ma'am.
Yes, sir.
Yes, ma'am.
Ma'am, there is some lagging.
Yeah, am I audible?
Yes, ma'am.
Yeah, okay.
Yes.
So I'll start with the first chapter, which I said is digital codes and binary arithmetic. Okay. So the flow of this chapter is something like this. I will first start with binary number system. Okay. I hope all of you are aware of this binary number system, but just as a review or as a revision, I will cover this part. Then I will start with various digital codes. After this, I will explain various ways to represent signed binary numbers. So here you are going to learn how to represent decimal numbers which are associated with sign in the binary form. Okay. And then next will be, once you know how to represent numbers in binary form, we will look at binary arithmetic. Okay. So starting with this binary number system, okay, the word binary comes from bi, which means two. Okay. So binary number system has two unique symbols, that is 0 and 1. And that's why its base is 2. Okay. In order to show that the binary number that belongs to, a number represented belongs to binary number, we write subscript 2. For example, if this is the number, if it is written 2 here, it means it is a binary number. Okay. Like decimal number system, binary number system is a positional number system, which means that every digital position in the binary number has some significance. Okay. There is a weight associated to every bit of binary number. Okay. This is very much similar to decimal number system, which you all are familiar with and we all use in
Ma'am, your
our
screen is not
daily life.
visible.
Screen is not visible. Just a second.
Yeah, ma'am.
Yes, ma'am.
See, it is visible
Yes,
now.
miss.
Okay.
Yes,
Yes,
miss.
now.
Yeah.
So I was saying that binary number system, similar to decimal number system, is a positional number system, wherein every bit position has got some significance. Okay. Now, as an example, if you take an example of a decimal number, let's say 257, this is a decimal number system. So I'm writing 10 over here, which means that base of the decimal number system is 10. Okay. What does it imply? It implies that there are 10 unique symbols available in this number system. Okay. So we know that this is a positional number system in the sense every position has some unique weight associated to it. Okay. We know 7 is in ones place, 5 here is in tens place, 2 is in hundreds place, which means that weight associated with this 7 is 10 raised to power 0. Weight associated with this number 5 is 10 raised to power 1. It is in tens place. Weight associated with this digit 2 is 10 raised to power 2. So it is in hundreds place, we say, right? So having knowledge of this, we know that we can expand, we can write this number in expanded form like this. 2 into 10 raised to power 2 plus 5 into 10 raised to power 1 plus 7 into 10 raised to power 0, which is 200 plus 50 plus 7, which means 257. So in order to find value of any number, what we are doing, we are multiplying each digit with its associated weight, and then we are adding all the products. So this is how we get the value of the number, right? Similarly, in a binary number system, each bit has a weight associated to it. Okay. As an example, let's take the same example, 1100. It is in binary. I have written base 2, which means this number system has two unique symbols, 0 and 1. So all the binary numbers will consist of only zeros and ones. Okay. So weight associated with the last bit is 2 raised to power 0. Now base is 0, so power is in terms of 2. Weight associated to next bit will be 2 raised to power 1. Weight associated to next is 2 raised to power 2. And similarly, this is 2 raised to power 3. The leftmost bit is called most significant bit because the weight associated with this bit is significantly going to affect the value of this number, right? It has the maximum weight in the sense, okay? And the rightmost bit is called least significant bit, okay? It has the least power associated to it, right? So the value of this binary number can be computed by multiplying each bit with its associated weight and then adding the sum product. Okay? So it will be 1 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 plus 0 into 2 raised to power 0. Right? So this is 8 plus 4. 0 multiplied by anything is 0. So you get 12. So 1100 in binary is equivalent to decimal number 12. Okay. So I hope this part is clear to all of you, right? Now suppose if you have a binary number which has which has binary point also. Okay. As an example, let's say 1100 and then binary point and then 101. This is in binary. What will be its value? So you see the digit bit just after the decimal point has weight equal to 2 raised to power minus 1. Next successive bit will have weight equal to 2 raised to power minus 2. This will have weight 2 raised to power minus 3. And the bits to the left side of the decimal point, you already know. It starts with 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So when you compute this will be 2 raised to power 3 plus 2 raised to power 4 plus 1 by 2 plus 1 by 4 plus, 0 into 1 by 4 and 1 by 8. So this case, what will you get? You will get 12 point, if you calculate this is 625. Okay. I hope this is clear to all of you. Maybe you all may be knowing this already, but this is just a kind of revision.
Yes, ma'am.
Okay, because it is very much important to have be clear with this concept. Only then you can we can proceed with the course.
Yes, miss.
Right?
Yes, miss.
Yeah.
Yes,
Okay.
yes.
Now another thing. Yeah. Let us also look at how to do counting. How to do counting in binary. Okay. Now, how do you do counting in decimal number system? We have 10 unique symbols in decimal number system. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So these are 10 unique symbols in decimal number system. In order to represent the larger numbers, we use combination of these unique symbols only, right? So how do we count? We start from 0 through 9 and then we are in short of the digits, right? So 0, we start from 0 up to 9 we write and then we are in short of the symbols, right? So what we do, we go back to 0 and we simply add 1 before that, right? And then we go on adding 1 to it. So you add 1 to 10, you get 11, add 1 to it, you get 12. And like this, we go up to 99. Okay. What you do after this? We are again in short of the digits. So what we do, we just go back to 0 again and we add 1 more digit to it. So you get 100. And then you just go on adding 1 bit to it, 1 number to it, and you get 101, 102, and like that. Okay. This is how we do counting in decimal number system. Similar thing we do while counting binary numbers. Okay. Let's see how will we do counting of binary numbers. Okay. So let me write decimal here, and this is binary. Okay. So we are looking at counting in binary. Okay. So we start with, we have two symbols in binary number system, 0 and 1. So first will be 0 and second is 1. So decimal number 0 in binary is represented as 0. Decimal number 1 in binary is represented as 1. Okay. Now we are out of the symbols because we know there are only 2 unique symbols in binary number systems. Now we do not have any other symbol. So how to represent decimal number 2? So simply following what we did while counting decimal number system, what we will do here is we'll simply go back to 0 and add 1 to it. Okay. So 1 0 in binary is decimal equivalent of number 2. Okay. You can verify this. You know how to find out value of a binary number, right? You know that every bit is associated with its weight. So weight of first, this least significant bit is 2 raised per 0. Weight of second bit is 2 raised per 1. So what you get is 1 into 2 raised per 1 plus 0 into 2 raised per 0, which means 2, right? 3 in binary is represented. You just add 1 to this such previous number. So when you add 1 to this 0, it becomes 1. So 1, 1. Okay. You can verify this also. Weight with LSB is 2 raised per 0. Weight with MSB bit is 2 raised per 1. So you get 1 into 2 raised per 1 plus 1 into 2 raised per 0, which is 2 plus 1 equal to 3. Right? So now we are out of the symbols. Now what to do? We have all the 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. So with 2 bits, we can have only these 4 combinations. I can write 0 as 0, 0, right? Isn't it? I can write this 0 as 0, 0. I can write this 1 as 0, 1. Right? Because it is not changing weight of this 1 bit. Right? If you write 0, 1, it is okay. Similar to decimal number. Number 5, I can write at 0, 5. If you append 0, before the binary number, it doesn't change the value of the number, right? Okay, now we are out of,
Yes,
now all the combinations are done. So next what? So we will again go back to 0 and add 1 here. Okay, so this is the binary representation of decimal number 4. Okay, now let us verify this also. Power of weight associated with LSB is 2 raised per 0. This is 2 raised per 1. This is 2 raised per 2. So 1 into 2 raised per 2 is 4 plus 0 into anything is 0 plus 0 into 0. So this is equal to 4. I hope it is clear, right? So 5 will be you add 1 to this number. So 100 plus 1 will be 101. 6 will be you add 1 to this. So 101 plus 1. If you add 1, so you get 110. Okay, and it will go on like this. So 7 will be 111. 8. Now with 3 bits, we can represent 8 numbers. Okay, from 0
we
to
can't
7.
see.
All the combinations are done now, right? So if you write 0 in 3 bit, it will be 000. 1 in 3 bit is 001. 2 in 3 bit is 010. 3 in 3
The
bit is
screen
0.
isn't visible.
If your video is paused,
Ma'am, video is lagging.
ma'am, your
Yes,
screen
ma'am.
lagging.
Okay. Wait.
Ishan Thanekar.
Just a second. I'll just remove the sharing and I'll share again. Now what is seen on the screen?
Nothing.
Nothing, ma'am.
Same thing?
Yes, ma'am.
Ma'am, it's still frozen.
Okay. Wait.
Mokshi, close your mic, please.
Darshil Modi.
Now,
Yes, ma'am. Better, ma'am.
Yeah.
can you see decimal number up to 8?
Yes, ma'am.
Right? Okay. So what I was saying is that with 3 bits, 3 binary bits, we can represent decimal numbers up to 7. Okay. Now all the combinations of 3 bit is done. So we are again out of the symbol, out of the bits. So what we will do, we will go back to 0 and add 1 here. Okay, this is how we represent decimal number 8 in binary. Okay, so I suppose it is clear how to do counting in binary, right? Okay, So one thing that is clear from this explanation is that when you have one bit, how many numbers are we able to represent? Anybody?
Two.
Two. You can represent two decimal numbers, 0 and 1 with one bit, right? You can represent two decimal numbers. With 2 bits, how many numbers
Four.
can be represented? 4. We can represent 4 decimal numbers. Okay. Why 4 decimal numbers? Because with two bits, you have 4 different combinations, right? You get 4 unique combinations with 2 bits, 0, 0, 0, 1, 1, 0, and 1, 1. So you can represent 4 decimal numbers, 0, 1, 2, and 3, right? With 3 bits, how many decimal numbers can be represented?
2 raised to 3.
2 raised to
9.
power 3, very good. That is 8 decimal numbers. Okay, so we can represent 8 decimal numbers. With 4 bits, you can represent 2 raised to power 4, that is 16 decimal numbers, right? So we can say that in general, if you have n bits, we can represent how many bits, how many decimal numbers?
2 raised to
power
10.
I hope this is clear to everyone. So when you have n number of bits, we can represent 2 raised to power n decimal numbers, right? Okay. Now you see, as I said, it is relatively easy to process digital signals as compared to binary signals, right? So the processing or computation of digital data is usually done or carried out in the binary form, okay? But the result is to be displayed in digital form, okay? In decimal form, right? So you see, if the output of computation is shown in the binary form based on the representation just I discussed right now, it will present problems. Okay? A better way would be to define binary codes for decimal numbers 0 to 9. Okay. What I mean to say by this is that if we are able to define decimal numbers 0 to 9 using some unique digital code, then we can represent any decimal number in binary form by using combinations of those binary codes. Am I clear? You see, I suppose you have understood the problem. Okay, you see, although I said processing is easy in binary form, and yes, processing is done in binary form only, but then at the end you have to represent it, you have to represent the output in decimal form again, right? So the easiest way would be to represent the output in decimal form, easiest way would be to define the decimal number 0 to 9 using unique digital codes. Okay? So with this principle, you can actually define or represent any decimal number by just having combination of those digital codes.
Ma'am, your video is paused again.
Yeah, I'm not writing anything anyway. So I suppose it is clear what I'm saying, right? So this is the advantage of having binary codes. Okay. See, otherwise, if you have to represent any decimal number, depending upon the size of the number of bits will change, right? Binary bits will change, isn't it? You require n number of bits to define 2 raised by n decimal numbers, right? So depending upon the size decimal number that you want to represent, you have to decide how many bits you have to use to represent in binary form, right? So one of the simple way to represent decimal number will be to use an approach wherein we will define unique digital code for the decimal numbers 0 to 9. And you know that any decimal number can be formed by having combination of these unique 9 symbols, 10 symbols, right? So similarly, any number can be represented in decimal form, sorry, in binary form by using combination of those unique digital codes. Okay, and that is the importance of having digital codes. Okay, different digital codes. So there are different digital or binary codes, and these binary codes can be classified as, let me just write now, binary codes. Is the screen seen now? So now I'm
Yes,
writing
ma'am.
on the
Yes, ma'am.
visible. No? So binary
Ma'am, there's
codes
a lot
can
of
be
lag.
classified into
No, ma'am.
Ma'am, your
Ma'am, it is
internet
stuck.
connection is weak.
weighted codes, non-weighted codes, alphanumeric codes, and error detecting and correcting code. So binary codes can be broadly classified into these 4 types. Weighted codes can again be classified into generally binary code and BCD code. BCD stands for binary coded decimal. Some of the examples of non-weighted codes are XS3 code and gray code. Okay, we are going to look at these 2 categories of codes. Okay, some of the example of alphanumeric codes are ASCII codes or EBCDIC code. Some of the examples of error detecting code is parity codes or parity bit and Hamming code. Hamming code. This is a broad classification of binary codes. Binary codes can be broadly classified into these 4 types: weighted codes, non-weighted codes, alphanumeric codes, and error detecting and correcting codes. Now let us look at the weighted codes first. Weighted binary codes are those codes that obey the positional weight principle. What I mean to say is that weighted codes are those codes wherein every digit position is associated with weight. Okay? So therefore, we have binary codes, binary number representation under weighted code. We know that we have already looked upon binary number system, and we have seen that it is a positional number system, right? So we can call it as a weighted code. Okay? Then we have BCD codes. There are large varieties of BCD codes available. For example, natural BCD code, which is also called 8421 code. Okay, 8421 code, which is commonly known as natural BCD code or straight BCD code. Straight BCD code. Okay, natural or straight BCD code. Then 2421 is another BCD code. Okay, then we have 5211. This is again a BCD code. So like this, there are large number of BCD codes which are available. Okay, we are only going to focus on majorly on natural BCD code, that is 8421. Okay. So let us look at this BCD codes in detail first. Okay. Fine. So the basic concept in the digital codes, binary codes, as I said, is to uniquely define decimal numbers from 0 through 9. Okay? Now, how many bits will be required to represent numbers from 0 to 9?
3.
You require at least 4 bits, right? We know that with 3 bits, if you have 3 bits, how many numbers can be represented? 2 raised to 3, which is equal to 8. So you can represent only 8 numbers, right? But we have to define, we have to assign a unique code to decimal numbers from 0 through 9, which means 10 numbers, right? 0 to 9 means 10 numbers. So we require at least 4 bits to represent, right? We know that with 4 bits, we can actually represent 2 raised to 4, which is equal to 16 numbers, right? But out of these 16 unique codes, we will be using 10 codes. Okay? We'll be using 10 codes to define each of these, 10 unique symbols. So each symbol will correspond to a unique 4-bit digital code. Okay? So this is the concept that was. Now let us start with BCD code.
Ma'am, you have muted yourself.
Sorry. Hello? Now I'm.
Yes, yes.
Yes,
Okay.
ma'am.
Okay. So before I start with this BCD code, let us take few examples of now binary representation. I have already explained you how to write value of a binary number, right? I had taken example of 1100 in binary, and we have seen that this is equal to how much? 12 in decimal, right? I suppose you all know how to convert decimal number into binary also. Okay? Let's say an example of 48, or let's say 12. 12 in decimal. If you are asked to convert this into binary, how do you do it? How do you do it? Anybody know? Because this is important. This will be required while performing binary arithmetic operations.
Modulus and divide it.
Yeah, ma'am, we will divide 12 by 2 and the
Divide the
remainder will
number
be fine.
successively. Divide the number by 2 successively, right? This is the traditional method. Okay? You divide the number with 2, right? And then you go on noting down the remainder, right? So 2 when divided with 12 will give quotient is 6, remainder is 0. You again divide this 6 with 2. So you get quotient as 3 and remainder as 0. You again divide 3 with 2 by 2 and you get quotient as 1 and remainder as 1. Then you divide 1 by 2, quotient is 0 and remainder is 1. So once the quotient is equal to 0, we have to stop, right? And then we write the remainder in the reverse order. So what you get is 1, 1, 0, 0, right? What will be this binary equivalent of decimal number 48? Do it at your end and tell me what is the binary representation of 48. Anybody got?
1100000 00110000.
Okay. So it is 110000. Right. Correct. Okay. Let me show you one more way to write the binary equivalent. Instead of doing this division, what you can do is, we know that the weight of each bit position is fixed, right? What is the weight? We start from the rightmost bit. Weight is 1. Then it is 2. Then it is 4 and 8, 16, 32, 64, and it will go on like this, right? Isn't it? So we know that the weight is fixed. Okay, weight at each digit position is fixed. The LSB bit has weight of 2 raised to power 0, which is 1. Next bit to LSB has weight of 2 raised to power 1, which is 2. Then 2 raised to power 2 means 4. 2 raised to power 3 means 8. 2 raised to power 4 means 16. 2 raised to power 5 means 32. 2 raised to power 6 is 64, and it will go on like this. Okay. Now we have to represent 48 in binary. Okay, so what we'll do, I cannot put 1 under 64, right? Because if I write 1 here, remaining all 0, it will mean number is 64, right? How do you find value of binary number? You multiply the bits with their associated weight, right? And then you add them, add the products, isn't it? So if I write 1 here and all zeros, it will mean number is 64, right? So I cannot write 1 under this. Okay. So I'll write 1 under 32. Okay. You can write 1 under the weight either equal to 48 or smaller than 48. So I will write 1 under 32. Okay. So 32. So we get 32 if we write 0 at all other bit position, right? But we want to have 48, right? We have to represent 48. So 48 minus 32 is how much? 16, right? So I want 16 more. So there is 16 over here. I'll put 1 here. And at rest all the bits, I'll write 0 because 32 plus 16 is 48. So this is binary representation of decimal number 48. Okay, I hope it is clear. Now you tell me 65 you have to write in binary form. What will be the binary representation of 65? So I will put 1 under 64, right? So 1 under 64, and then I want only 1, right? 65 minus 64 is 1. So I want 1. So I will put 1 under this one. Okay. So it will be 1. Then under 32, I'll write 0. Under 16, 0. Under 8, 0. Under 4, 0. Under 2, 0. And then 1. So this is binary equivalent of decimal number 65. Okay. I think this is clear to everyone. This is one of the fastest way to find out the binary equivalent of given decimal number. Okay. Okay. Now coming to BCD codes. Okay. BCD codes now. So let us write down BCD codes now. As I said, BCD codes are the codes, digital codes, wherein decimal numbers 0 to 9 are uniquely defined by 4-bit binary. Okay. So let us write decimal number from 0 to 9. Okay. And we will write BCD equivalent. Okay. BCD equivalent of these decimal numbers. So 0 in BCD. Now I'm writing straight BCD code. Straight BCD code means 8421 code. Okay. Now here 8421 implies weight associated with the bit positions. Okay. So the least significant bit will have weight of 1. The next bit will have weight of 2. Next one will have 4. Next one will have 8. If you relate this with the weights associated with any binary number, as I said, it is 1, 2, 4, 8, 16, 32, 64, and it goes like this, right? So our natural BCD code uses, or in a natural BCD code, the decimal numbers 0 to 9 are represented using the straight binary representation of these decimal numbers. You see, if you look at the code, the first 4 weights are 8421. Okay, and in a natural BCD code, I said it is 8421 code. What does it imply? It means that in 8421 code, the decimal number from 0 to 9 is represented by its straight 4-bit binary equivalent. Okay, you know that 0 in binary is 0, 0, 0, 0. 1 in binary is 0, 0, 0. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. 8 is 1, 0, 0, 0. And 9 is 1, 0, 0, 1. Right? So 8421 code means each of these decimal numbers from 0 through 9, they are represented by their straight binary form. Okay? You see, in binary also we write 0 as 0, 0, 0, 0 in 4-bit representation. Binary equivalent for decimal number 1 is 1, which means in 4-bit if you write, it will be 0, 0, 0, 1. 2 is 0, 0, 1, 0, 3 is 0, 0, 1, 1. I suppose this is clear, right? So these are so in BCD code, you know, these 9, 10 symbols, 0 through 9, they are uniquely represented by the corresponding 4-bit binary equivalent.